Yeah, hello everyone here in the room and also to the audience online to the battery breakout session. My name is Roman Buchheit and I will guide you through this session the next 2 hours. And first of all, I want to start with the electrochemistry and the battery team at Math to Market. I thank my colleagues very much who helped to contribute to the content what I will show in the next half hour. In the electrochemistry team, there is Steffen also here in the room, and Ilona. She is in the hydrogen breakout session, so she cannot be here now. And then we have Janine, who is in the support team, so she is in the workstations. When you want to test GeoDict 2025, you can go to her. And we have our developers, Fabian, Sebastian, and Sven, and also the developers in ITWM who are doing the best solver. Falco is here in the back. And then also Jochen Zausch and Jan Lamme. Yeah, I want to show you very shortly the timeline for the breakout session. So after the welcome, there will be an introduction into the new possibilities of GeoDict 2025 and battery simulation. And after that, there will be a talk from my colleague Max, and he will present the development of a validated simulation model for all solid-state batteries. Then there will be a short break. And after the break, I'm very happy that we will have a talk from Robert Mücke from Forschungszentrum Jülich, also about solid-state batteries, but more focus on mechanical properties. And in the end, I want to end with a live demonstration, how you can set up a simulation with lithium concentration-dependent parameters with GeoDict 2025 and why this is important for some simulations. Okay, yeah, I want to start with just a general introduction. Why do we sit here? Why do we think about batteries? And this is just a market projection of the battery market until 2030. And batteries are very important for different applications. You have the consumer batteries in household devices, but then also other forms of batteries like these coin cells or the lead-acid batteries that are well known in cars. But then also, of course, lithium-ion batteries. That is maybe the most important battery technology nowadays because you get the highest energy density. And you see here that the market is expected to double until 2030. So there is a large potential here. And this market is booming. So I just looked up some headlines of the past month. And then you can see there is a lot of news going on. So the demand is growing, but also the materials used in the battery are sometimes critical. So you want to make good use of the raw materials inside of your battery. Then there is new technologies coming up, the sodium-ion battery, for example, but also silicon anodes. We have seen in the morning in the plenary talk from Professor Lee some work on silicon electrodes also. And of course, also solid-state batteries are under investigation. They have some advantages, but also challenges. And then to get more practicability, people also try to go into fast charging and also high voltage battery packs. And yeah, it's very booming, but as you can see, a lot of news and competition in the market. And some companies also say it's too risky. So that was an example from a company who said, yeah, they don't want to go that step to really get into the market. because if you want to catch up, you need to be really fast in the development, and the investment costs are also high. And we think here the digital material design can really be of help, because with digital material design, you get fast results, so you have a shorter time from research to the market, and you can test in digital experiments many different technologies. You can test many different parameters in the battery, like different chemistries, different particle sizes, different geometries of the electrode. And you can do a lot of this digitally and then focus your experimental approaches to the promising prototypes that you find in the simulations. So with digital material design, we believe that you can reduce the costs and also the risks in this battery design process. And this enables you then to adjust the battery to the application that you have. Like, for example, now for grid stabilization with a lot of renewable energies in the electricity system, you want very large batteries like a container from a ship. And this is for grid stabilization. So in the evening, for example, when no light is shining, the battery gets discharged and stabilizes the grid. And here you want high energy density and low cost with a high capacity. But also because it's a large battery, it should have, of course, high safety. For mobility applications like electrical cars, you have maybe another focus on high charging speed, because if you have a break, you don't want to wait too long until you can go on again. And the well-known batteries from consumer electronics, like here the laptop computer or also cell phone, there you maybe want to have first a high energy density because the device should be small, and still you want a good battery life, but also a good life cycle stability, because a phone, for example, is doing a full cycle every day, and you do many more cycles in 1 year than when you have an electrical car, because usually you don't discharge the complete battery of the car every day. And we have many companies already making use of digital material design with GeoDict. And yeah, there are just some of them are on this slide, but maybe I want to focus on this statistics I have seen. So that is the 7 biggest battery cell producers. And I'm very proud that 5 of them are also using GeoDict to improve their products. And yeah, I want to show you now what you can do with GeoDict and battery research and battery development. And I think you all know roughly how a battery works. And here you see a microstructure of a LFP cathode. And that is a FIP SEM 3D scan of the electrode. And when you segment the scan with GeoDict, you can distinguish all the different components. So you have the active material, you have the electrolyte phase, and you have a binder and carbon black network for mechanical stability, but also for the electron conduction network. And it's very similar like when you imagine a city with a complicated traffic. You have some spaces where pedestrians can walk. If you have a river, then there are big ships on the river. They are very slow, but they can transport a lot of material. And then you have cars in the driving way. And in order that the traffic works well, all the different parts need to be adjusted. So there must be enough space for all of the different components. And very similar it is with the battery. So the lithium ions need to be to move in the active material. There is diffusion in the particles. Then the ions are transported in the electrolyte phase from one to the other electrode. And the electrons must reach the active material from the current collectors via the CBD network. And that all this is really working well together, you need to improve the microstructure. And that is what you can do with digital material design. And the question is now, how do you start this? And I want quite shortly show you how you can digitize a scan. It was already mentioned this morning. So when you have a FIB-SEM scan, you have secondary electron image. You can do segmentation with AI tools, only using a single image stack. But here in this example, you see that there are still some errors in the segmentation. So here there is some active material segmented in the binder network. And what you can do, since the last GeoDict version, you can use 2 image stacks, so also the backscatter electrons. And by using the secondary and the backscatter electrons, the AI segmentation is combining both informations, and then the segmentation result is getting better. Then we are also working on the method to create a 3-dimensional microstructure from a single 2D image. And for this, we have now 2D to 3D GeoApp and the new GeoDict 2025. What you can do here is you create only one single 2D cross-section image of your sample. That is much cheaper and easier to get than a complete 3D scan. And what the GeoApp is doing, it's analyzing the segmented 2D image, calculating the statistics from this 2D image, and then creating a 3-dimensional digital twin. And then in the result, you get the difference in the 2-dimensional statistics of the digital twin and of the original image. And then you see here that this matched quite well. So all the errors, pore size distribution, granulometry, and so on were 12% or less. And because we took this image from a complete 3D scan, we could also validate the digital twin in 3D against the scan in 3D. And by comparing the tortuosity in the electrolyte space, you see that also this tortuosity matched quite well. That was an example from a cathode electrode with NMC particles, but we did the same also with a graphite anode. So we have a single image from a graphite electrode, and then the GeoApp will create from this single 2D image a digital twin in 3D using the statistics from the 2D image. And also here the tortuosity between the digital twin in 3D and the complete scan in 3D matched quite well. So you can try this out now yourself in the new GeoDict version. Okay, but what can you do now if you have microstructure of the electrode inside of GeoDict? And just to show you the potential of the microstructure optimization with digital methods, I just want to stress out the question of binder content in a cathode, because here you have a classical problem in material science. When you increase the CBD phase, so more binder and carbon black in the sample, then the electrical conductivity of the electrode will go up. But at the same time, you have less pore space available and the ion transport will get reduced. So the ion diffusion inside the electrode goes down when you have more binder. And the question is now, how can you trade off between these two different properties of the electrode? Because you need both. You need good electron conduction and you need good ion diffusion. And what you can do with GeoDict, you can just check how is the capacity of this cathode structure with different binder content when you do a 2C charging until 4.2 volts. And if you do this with GeoDict, within 1 day, you get all the different data points here. And then you see here, the best result was at about 2.5% binder content for this example. And that was just in 1 day using simulations. And if you would do the same in a laboratory, then you would need several weeks to prepare all the different electrodes and then do the electrochemical experiments. So this can accelerate your development quite a lot. And in the end, you get 0.5% increase in the cell capacity compared to the initial value. And first you might think, okay, this is not so much. But if you think you have a large battery factory, for example, Tesla has the Gigafactory close to Berlin, and there they produce 100,000 electrical vehicles a year, and they need about 100 million cells for all these electrical vehicles. And when a single cell has 0.5% more capacity because the microstructure is improved, then they can save around 450,000 cells a year, and this means you have almost 7 million less dollar you spend. So there's a big potential in this because the scale effect is quite large when you go to a production level. Yeah, how can you generate the different microstructures? And here I only want to shortly mention our structure generators in GeoDict. So we have granular structure generators and also GeoApps for this. There are GeoApps to create anode structures and also cathode structures. And with these GeoApps, you can just create with the mouse click microstructures here with different areal loading. So high area loading would be for higher energy density and lower area loading more for high power application. And yeah, it's very easy with these GeoApps to create the microstructures. Okay, so far I have talked a lot about how can I get the microstructure. You do the segmentation of a scan, you use the 2D to 3D GeoApp, or you create the microstructure with the structure generator. But what can you do then when you have the microstructure? And you can analyze different physical properties in order to improve the reliability and safety of the battery. For example, your customer asks for a certain lifetime of the battery, so you want to have control of the degradation mechanisms. Or you also want to have a safe product, so you don't want that there is any issue with the battery during operation and that it catches fire or something. And for this, once again, the microstructure is a key, because if you know what is really going on the microstructure level, you can also evaluate what are the risks for degradation mechanisms or possible security issues. And yeah, I will just show you some of the new things that we introduced into the new GeoDict 2025. One of them is the heat production inside of the battery. So here you see a graphite NMC battery, and it is charged at 1C charging rate from 3.5 volts until 4.1 volts. Yeah, during this charging, of course, a lot of energy will go inside of the battery. But part of the energy that you put into the system will be dissipated into heat. And the question is, where does this heat come from? How much heat is produced? And here we have now a new feature. You can see now the produced heat inside of the battery. And you can see the heat power over time in the different components of the battery. So how much heat is produced in the cathode, how much in the anode, and how much in the electrolyte phase. And you do not only get this plot over time, but you can also get the 3D information. There you can look on the details and not only have a look on the average heat produced. For example, if you look on the electrolyte heat, then you see here that there is one hotspot here close to the separator where you have some bottlenecks, so all the ions need to go through this small section. And here you have quite a lot heat produced. The anode active material, graphite, has most of the heat on the surface of the graphite particles towards the electrolyte, because here the ion exchange is taking place. But most of the heat is produced in the NMC particles, because here you get the concentration gradient and then the diffusion of the ions. So this allows you to learn much more details, and also you could, for example, try to improve the microstructure that the total produced heat is less. Another degradation mechanism is the mechanical degradation. And how can you imagine this? So if you have a car and you go with your car into a car park, and you do this many times, like you go to work every day, then at some point you might hit a wall and then you have a small scratch on your car. And when you are in a hurry and you do the parking not carefully, but you go very fast in the car park, then you have a higher risk that you have such a damage of the car. And very similar it is also for the battery, because with every charging and discharging, you introduce lithium ions into the active material and you release it again. And all this insertion of lithium ions will lead to an expansion of the volume and to a shrinkage. And if you do fast charging, then even this mechanical stress is larger on the active material. And with the battery degradation module, you can visualize the mechanical stress and strain due to intercalation of lithium. So first you do electrochemical measurement, you know where is lithium ion concentration change, and then you do the mechanical simulation, and then you know, okay, I get this stress and strain inside of my structure. And one important feature that we were asked in the past were the boundary conditions for this module, because so far it was not possible that you have a certain defined external stress or strain on the volume domain that you simulate. But for example, the all-solid-state batteries, they are always operated at a certain external pressure. And now in GeoDict 2025, we have a new boundary condition for the battery degradation, that you can put an external stress or external strain on your structure while you are doing this battery degradation simulation. Next, I want to show the degradation mechanism lithium plating. So what is lithium plating? This occurs especially when you have fast charging. Then it might be that locally you don't insert the lithium ions into the anode material, but you plate metallic lithium on the surface of the anode material. And in the worst case, you will get lithium dendrite growth and maybe even penetration of the separator, and then you have a short circuit, and it could be that the battery is on fire, and this you don't want. So it's good for you if you know, can I estimate the risk of the lithium plating at certain conditions? And here you see very fast charging simulation. So it was 3C charging rate. This means in only 20 minutes you fill the complete battery from empty to full. And you can visualize the plating potential on the surface of the anode active material. This is the local potential between the electrolyte and the active material. And if this potential is below 0, then you know you have the thermodynamic requirement fulfilled for lithium plating. And as lower this value is, as higher the risk of the lithium plating is. And here you see that the highest risk of lithium plating was close to the separator. So this helps you to to estimate this risk and also maybe improve the microstructure to reduce the plating potential. Okay, so I showed you different possibilities to look on the details of the three-dimensional simulations of the batteries. And the question is now, okay, how can you perform the electrochemical simulation with GeoDict? And we have, in general, two different models implemented inside of GeoDict. So what I was talking about so far was the fully resolved model. So you do the simulation on the three-dimensional microstructure. We have two different solvers there, the LIR solver and the best micro solver. And you get all the details on the three-dimensional structure. But the problem is that this is quite high computation effort. So, for example, when you look on this example structure and you do the charging from 3.5 volt until 4.1 volt, this took around 9 hours with the best micro solver and needed about 65 gigabyte of memory. And the classical model often used in battery development is a homogenized model that is a Newman model. And you simplify the simulation to a one-dimensional problem because basically the ion transport is going in this direction. And the good point of this method is that you get results very fast. So with the homogenized model, the calculation time was only 20 minutes. And also the memory was much less, so only 2.3 gigabytes. And the charging curve of both different models is quite similar. But the important thing to use the homogenized model are the effective parameters. So you need information because all these electrodes are homogenized. You need information. How's the effective electron conduction in the electrode? How's the effective ion conduction and so on? And the question is, where can you get these parameters from? And here also GeoDict can help you because you have the fully resolved three-dimensional structure inside of GeoDict. And if you do a homogenized charging simulation, then GeoDict will calculate all the different effective parameters for the anode and also for the cathode. And it will also report all the calculated parameters in the result report. And these parameters are then used in the best meso solver for the charging curve. But of course, you could also take the effective parameters that are calculated. And if you have your own in-house Newman model with some adjustments, then you can also use these parameters calculated from BatteryDict. And this is a good way if you want to test many different microstructures, then you can do parameter studies. You get very fast the charging curves. And if you have one microstructure that looks very interesting in the homogenized model and you want to know more about it, then you can do a fully resolved simulation on that microstructure. Then we have some new features in the electrochemical simulation. And one of them is that you can now use up to 4 different materials for carbon binder network or also for conductive additives in a single electrode. So far, it was only possible to use one material for the CBD phase, for example. And what can you do now with the new possibility? So it's known from the literature that the conductivity in the CBD phase is not the same all over the battery electrode, but due to the fabrication process, you have a gradient in the electronic conductivity. And you can now use 4 different material IDs to represent the areas with higher conduction and lower electron conduction in the CPD phase, and then perform electrochemical simulation. Or you could say, I have core shell particles, like particles with coating, for example, ion conductor or so. And that would be this yellow, the yellow coating on the gray active material particles. And then you have still the CPD phase as the red material ID. And yeah, you would then use both in the electrochemical simulation. Or you can say, I want to use active material. I have my CPD phase, that's the red part, and I have conductive additives, for example, vapor-grown carbon fibers. And you can simulate such a structure now because you can use up to 4 different additives in the charging simulation. Then we have some smaller adjustments. With the new GeoDict 2025, you get the full control what volume fields are written into your result. So you can select here in the output tab the different physical properties, and then you can save hard disk space because you only save what you really need. And we improved the output. So if you enter all the mass densities of your materials, then you can get the cell potential curve also as a function of the mass cell capacity, which is useful if you want to compare it with experimental data. And with this, I want to end my talk with a short outlook, what we plan to do next. So there are many different things we are working on. I maybe only focus on some of them now. Together with our partners from ITWM, we are working to also bring electron chemical impedance spectroscopy into GeoDict. First, it will be an expert setting, but later we also want to have it in the GUI. Then we also work on the electrolyte saturation. So when you fill the electrolyte into the microstructure, that you get a time dependent saturation. And we are working on all solid state batteries. That will be the talk from Max, who comes next. And in the end of this session, I will show you concentration dependent parameters. At the moment, you need an expert setting for this, but in the future, we want to make it more easy that you can use it from the GUI. And with this, I want to end this first talk. Thank you very much for the attention. You can always ask me if you have questions about this, or book a meeting with me. And yeah, if there are any questions now, you can ask, and thank you.
So thank you very much for the introduction. My name is Maximilian Luczak. I'm with the consulting and projects team at Math2Market. And for this particular case, I work with a couple of partners in the publicly funded project Delphine, which is aiming to develop a validated simulation model for all solid state batteries. First of all solid state batteries are a relevant topic in battery development at the moment. You get news about battery breakthrough 600-mile charge in 9 minutes, a 20-year lifespan, which is quite something big that you can promise, and higher proof EV batteries. So solid state batteries being able to run without the flammable electrolyte, which is all great news to get. And of course, this all solid state battery technology has a lot of promises. And here we will take a look at our approach in this project. to tackle the both potential benefits, but also take a look at potential challenges that you will face when developing these kinds of batteries. So as a cornerstone for future or modern infrastructure, portable electronics, and energy systems, ASSB technology could be of a great benefit with the enhanced safety factor. You don't have any flammable electrolytes in it. You have a high energy density and also the promise of improved longevity. It is just overall a great potential that you want to harvest. But the challenges, of course, are also there. You have potential issues with the interfaces between the solid electrolyte and the active material. The manufacturing can be quite complex. Most of the materials used in the solid electrolytes are both not hydrophobic, but very sensitive to humidity as well as oxygen. And the materials that are used at the moment may also be limited, so you may want to look into different materials that you can use for this technology. And all in all, smart methods and research and development are very important to make this endeavor a successful one. Here I want to talk about the approach we go for in the Delphine project. First of all, we had to make sure that we understand the solid electrolyte, which we haven't really used before in GeoDict. In this case, we settled on LPSCl, and in combination with NMC 811, we picked LPSCl since it is a commercially well available solid electrolyte, even though it has some features, especially in the imaging qualities, that make it a little bit inferior to, example, LPSCI, the iodine salt. We still wanted to use the LPSCl in this project because we think it will be more probable to be used in a real-world scenario. We wanted to develop a way to digitalize these these kind of structures in a more reliable way. So at the moment, as Roman talked about, having a 3D scan of these structures usually requires FIB-SEM technology. FIB-SEM is quite expensive. It's quite difficult to get your hand on. And so we wanted to also move forward a way to use more available methods like micro-CT scans. And of course, we wanted to take a look at what the batteries actually can do that we want to simulate, or what ultimately which we want to also produce in this project. So we needed a good and solid way for BatteryDict to handle the solid electrolyte. So this is an overview over what I would call a typical workflow that you will have in GeoDict. Step one is that you have to digitize your material, both to understand your material better, but also as a starting point for your material development. You need to know where you come from if you want to improve the material that you have. So we have a dedicated sub-project which is taking care of producing good scans of the cathode materials that are used in this project. Secondly, we want to analyze the scans that we have. We want to understand as much as possible about the materials that we're using. Fortunately, GeoDict already has a wide array of analytics that we can use to tackle this problem. And so we get the statistical data as well to create a digital twin. The third step would be validating our results with experimental data. Fortunately enough, we have an experimental group in this project, which is providing us with both input parameters, which we use to design our materials in GeoDict, and also they provide us with results which we can then lay against the results that we get out of GeoDict. And the last, also very important step is that we actually need to be able to design new kinds of cathode materials. For this is imperative if we want to make use out of GeoDict, because we want to improve the material that we got. So we are working on a cathode designer which specifically is geared towards the use in all-solid state batteries. This morning you already heard of this approach by Dr. Orkun Furat from Ulm University, who is part in this project. And if we take all of this together, that we can understand our materials, we analyze them, we can validate it, and then design new materials, and can, so to say, drive the loop again and analyze the new materials, see where we can improve, then we are actually doing innovation with the help of GeoDict into creating better materials for the future. So let's go through these steps one at a time. So first, about the digitization. Here we work together with a commercial partner. It's called RJL Micron Analytics, and they provide us with micro CT data of the materials which were produced by our partners at the Justus Liebig University in Gießen. And what we needed to do is two things. So first of all, the micro CT resolution is right on the edge of what you can use for this problem that we are facing here. And we needed a solid way to improve our image quality. Fortunately, RJL is able to provide us with two different reconstructions of the same scan. So we have the standard scan, which gives a good topographical resolution, which is here seen on the left. And we have a free field phase contrast reconstruction of the same scan, which is basically giving us a better contrast between background and other components which we find in the solid state battery. In this case, this is important because the as you can see, the contrast between the LPSCL is not always very high against the other materials. So we are very happy that we get these two different image stacks to use in this segmentation approach. So what we are doing is we basically take these pictures into our software. In this case, I started to train a UNet 3D model, AI model, to segment this. You can see you basically just mark your areas depending on what you believe they are. So you can see the pore is unfortunately light gray, which is really bad with the other contrast here. But in red, we have the active material, and in green, you will see the solid electrolyte. This is kind of hard to do when you only have one scan, but if you can switch back and forth between the free field contrast and the high resolution scan, you get a better idea what you're actually labeling. And in the end, we can take the segmentation of both channels, the standard and the free field contrast, and put this into a dual channel segmentation. It's basically the same approach that Roman showed before regarding the secondary electron images he used for the FIBSEM. So you can see, maybe I put your attention on this spot here. This is, when you see it with your eye, you can pretty easily indicate that this is probably void space. Unfortunately, the single channel segmentation didn't agree with my eye test on this one, but if we use the dual channel segmentation, have the free field phase contrast image in the segmentation as well, we get a way better result. So in the end, we can take the relatively cheap and easy micro CT scan with two different reconstructions, and through the use of the dual channel approach, we are able to enhance our image quality significantly. Of course, this is still work in progress. The pictures that you see right here are taken from a powdered sample. It's not a compressed cathode sample yet, but we will have this in the near future. And then we can work again on the improvement of this imaging technology towards a better understanding of the cathode. So here I have two images. So this is the powder one that I just showed you, which has still about 25% of void space or empty air inside of the structure, which is of course not what we want to have. So I also had, fortunately, I had a FIBSEM scan of a all-solid-state battery from the same group in Gießen, and this one was a compressed structure, so we see 7.2%. This is much more what we would aim for, but I'm fairly confident that with the compressed structure and the micro CT scan, we will actually be going towards the same boundaries in this case. So for the further slides that I show, I have used the FIBSEM scan because this structure is just way more representative of a actual ASSB cathode. So let's go to the analyzation part. Fortunately, here we can use lots of features which are already inherently in GeoDict. So we can take a look at lots of geometric parameters. We have the porosity, pore size distribution, grain size distribution, surface area, length of contact lines, tortuosity. These are all geometric parameters which we're very confident that they are calculated correctly given the structure that we got. We have lots of transport parameters. We can predict the conductivity, the diffusivity, lithium path of single particles. We can do all these analysis on the structure that we have available. And finally, we can also look at the way the structure behaves in a battery. So we can have the charge curves with different charge rates simulated on the structure, the 3D lithium concentration during operation. We have fast simulation using homogenized models and instant estimation of charge curves. So this is what we can all do with the structure once we got it. So we already gain a way better understanding of the structure and of the properties of the structure immediately from this. So again, I have to show a work in progress slide. So we have implemented all the necessary steps that you need to put into calculating all-solid-state batteries with BatteryDict. Here's an example of experimental data, which we get provided by the Justus Liebig University. And here's an example of just 3 charge rates on the same structure, which we used in this case here. So the new features which you will have in GeoDict. So currently, the solver equations have been modified to work better with solid electrolytes. So the fusion and migration terms are not required when you look at ASSBs. So as soon as the as BatteryDict detects that you're using a solid electrolyte, we will switch to the required calculations that have to be done. The transfer number T plus is always 1. So charge conservation and electroneutrality terms are also simplified. The exchange current density between the active material and the solid electrolyte is implemented in the material database. So when you, for example, pick NMC811 and we have the available data with us, we implement this into our database. So you can add, you can pick LPSCl as your electrolyte with the maximum exchange current density, which we have evaluated for this substance. And of course, you can also add your own electrolytes into this calculation. So these materials, namely NMC811 together with LPSCl, will be shipped with GeoDict 2025 and allow you to do the simulations in BatteryDict. So this is more of the technical terms that we did to improve this. So we, in general, exchanged the Butler-Former rate constants, which were present all over the battery dict GUI. We replaced this with the maximum exchange current density. So this is a bit more of a approachable, let's say, unit. You have ampere per square meter, which is much easier to understand than something like the square root of meter times second times whatever the Butler-Former rate has in its unit. So this is, I think, an improvement just for understanding the calculations that are going on. In this case, you can see how we fitted our maximum change current density against data which we got from Anja Bielefeld from University in Gießen. So we take this data, we analyze it, and then we put it into the material database. Of course, it has to be said that you need to put in this information with every pair of active material and solid electrolyte. Okay, these are some of the equations which get simplified, which I just mentioned beforehand. So this is the ASSB cathode generator, which has been presented by Orkun Furat from the University in Ulm before. This will be available in GeoDict 2025. So it will be shipped with GeoDict and you can use it and take a crack at it yourself. With the new model structure. So on the left, you see the digitized structure. This is the model structure by Orkun and his colleagues at Ulm. We can see, I think the resemblance is quite big with these two. So it's a good representation that he found. And the virtual model is going to be a parametric one. So in our final aim of this is that we allow you to really take a identify the different grain sizes and that you have a parametric model where you can say, oh, let's say my grain size distribution is a little bit on the larger side. What effect does this have on my battery simulations? So this is an important step that we not only got one model that works with a couple of AI-infused parameters, but these are actual parameters that you can put into your research. All of this has been collected in a publication that we did together with Ulm University, and it is submitted and will be available soon. With that, I want to thank our collaborating partners in Gießen, Ulm, and RJL Micron Analytic. I want to thank the Federal Ministry of Education Research for funding this project. And I would like to answer any questions if you have some. Thank you very much.
Good, yeah. Now we are already reaching end of the breakout session. And I want to end this with a short live demonstration. And yeah, I want to talk about concentration-dependent parameters in the electrochemical simulation. And this can be quite important in some cases. I just want to motivate this with an example from literature. So here you see a study from NMC 622 cathode half cells, and there were C-rate tests at different C-rates. That is these points here. And you see that especially at high C rates, the voltage drops quite fast towards the end of the discharge. And in this study, there were also electrochemical simulations performed. That is the lines. And yeah, if you want to get a quantitatively comparable simulation result to the experiment, then it can be necessary to consider the lithium concentration dependent properties of the active materials and of the electrolyte. And yeah, this is actually the reason also for this very fast voltage drop towards the end of the discharge. And I want to show you now how you can set up a simulation with GeoDict 2025 using the lithium concentration dependent parameters. And there are two different kinds of materials that have or can have lithium concentration dependent parameters. First, there are the active materials. And for the active materials, the lithium diffusivity and also the electronic conductivity can be depending on the lithium concentration inside of the active material. And you can set up this in the simulation by using an expert setting. And the other component in the battery that can have concentration-dependent parameters is the electrolyte. There it can be the ionic conductivity, the diffusivity, or the transference number. And here you can set it up in the graphical user interface. And yeah, I just want to mention that this is at the moment possible if you use the best solver in BatteryDict simulation. And yeah, we are working that we want to implement it also for the LIA solver, so the other solver in BatteryDict. Yeah, and let's get a bit more specific for the example I mentioned before. So we have a cathode with NMC 622. And if you look on the data for the diffusivity of the lithium ions inside of the NMC, you can find such a property as a function of the lithium concentration inside of the lithium particle. And you can see that if you have a low lithium concentration, then the diffusivity is around 4 to the power of minus 15 square meter per second. But here, when the lithium concentration is very high, then this diffusivity is dropping strongly, and it's 1 order of magnitude less than at this lower concentrations. And the first challenge is to get this data for your simulation. And you need to rescale it. So you need the data as a table in a text file. The first column is the lithium concentration, the removable lithium concentration that is between 0 and Cmax. And the other would be the diffusivity. And if you want to know how you get these text files, we prepared for many of the active materials that we ship with GeoDict the text files already. You can just write to support@math2market, and then we can send you this. And also we have PDF instruction that we can give to you if you measured your own material in the lab and you want to know how do I set up the text file, then yeah, you can also ask us and we can provide it to you. And after this, I want to show it how this looks in GeoDict. So I open GeoDict 2025. And first I want to open the structure. It's a cathode structure that I created with one of the structure generator GeoApps in GeoDict. I change the colors a bit. So we have 3 phases. We have NMC 622, the active material in gray, the CBD network in red, and the pore space that is filled with the electrolyte. And I already created a charging curve using the homogenized model. And yeah, it looks like this. So it was starting at around 3.9 volts and then discharging until 3.4 volts. And the charge rate here was 3C, so it's quite fast discharging. And this is how the discharge curve looks like when you use constant parameters for the diffusivity of the NMC. And here we see this looks a bit different than in the experiments because this voltage drop in the end is not so strong. And now I want to show you how you can do this simulation when you use the lithium concentration dependent diffusivity. And for this, I have the file with the concentration dependent diffusivity prepared already. So it looks like this. It's just what I showed before in the PowerPoint file. So the first column is the removable lithium concentration. It moves between 0. So this means it's fully delithiated and you have the highest OCV voltage towards the Cmax value of the NMC 622 with 33,000 mole per cubic meter. And in the second column, you have the diffusivity values for all the different lithium concentrations. And you take this text file and you can copy it to your project folder. So that's the project folder of GeoDict. And we will soon need the file name of this text file, so I copy it already. Good. So now we need to set up the expert setting that in the next charging simulation we use the concentration dependent diffusivity from this text file. And for this, you go up here in top to settings and then edit expert setting. And here you need to first name the command that you are using. We are now using electrode charging. So it's charge electrode command in the BatteryDict module. So first I select here BatteryDict module. And then here the charge electrode commands. The same would be if you do a full battery, then you would select charge battery. And here we need the key cathode active material 1 lithium diffusivity file. Because we have only one active material, of course, you can also have an electrode with different materials. Then you can also provide different text files here. And in the end, I enter the file name of our text file. Because I copied the file into the project folder, it's enough just to provide the file name here. But just to mention, you could of course also provide the file path if the file is in another folder, or also relative path is supported here. And then you just click OK. And now GeoDict knows when it's performing the next charge electrode command that it will use this concentration dependent diffusivity. So what I can do now is I just load the settings from my first simulation into GeoDict. So I click here in the result viewer to load input parameters. And then all the parameters from the first simulation are taken over. I go to battery dict and then electrode, charge electrode. When I open the settings here, we see the different configurations. So that's the materials we are using. And here it's just as before, we have 3C charge rate, so quite fast. And the simulation is stopped at 3.4 volts. And we are using the homogenized model just because it's faster now here in the live demonstration. But I will change here the result name that we can differentiate to the original result. So I say the result, this is with concentration dependent diffusivity of the NMC. And then we are done here. So I click OK and then charge. Yeah, now it will start. To first calculate the effective parameters for the homogenized model. It's just what I said in the first talk. So here it's now calculating the effective conductivities. And after this, it will calculate the effective diffusivity and so on. And for the diffusivity, it will take now the concentration dependent values that we provided in the text file. Okay, so it's done with the conductivity. Now it's calculating the diffusivity. And just to mention it, you can also use this with concentration-dependent electrical conductivity. Then you have a text file with the concentration information in the first column and the electrical conductivity of the NMC in the second column. But this only works with a fully resolved model because you need, of course, the information of the local lithium concentration inside of the particle, and that is not possible with a homogenized model. Yeah. Good. So should soon be finished, I think. Still calculating the conductivity. Yeah, this is running on the laptop, and yeah, I know always when I have Teams running at the same time, it's a bit slower than when I run it before, yeah. So it's about double runtime when Teams is running at the same time. It also works in 2024, yeah. So since 2024, we have this feature. Okay, now it's done with the effective parameters, and now it's running the P2D model, so calculating the charging curve. And this is actually quite fast because it's the 1D problem only. And yeah, now it's done. And if you click both results here and this sync tabs, you can have a look here. And you already see this voltage drop towards the end of the simulation is much more prominent. And if you want to compare it, you can also click here, combine results. And here you see it quite clear that here in the end, towards low voltage, when the NMC is close to fully lithiated, you have less diffusivity and faster drop of the cell voltage. When you look in the overpotentials tab, you can see that the difference is mainly here to the diffusive overpotentials. So I can only show this. Oh, that was one. It was resistance here, diffusive. So yeah, here you see the difference. So towards the end of the simulation, with the concentration depends, so that is this curve in dark blue, the overpotential is much more prominent than when you use the constant diffusivity. Yeah, and that was already everything I wanted to show. You can do the same with a fully resolved model, also using concentration-dependent properties in the electrolyte. And yeah, this is very helpful if you want quantitative comparison between experiment and simulation. Then very often you need to consider this more complex setup with the concentration-dependent properties. Thank you very much for the attending the session, also you online, and there will be now a kind of poll in the chat, so you can give feedback when you are online, how you liked the conference so far. And yeah, thank you very much. There's time now for discussion or have something to drink. Thank you.